right, so let's get started. Let's look at the x values, the y, the kind of the coefficients of the y terms, and the coefficients of the z terms. And for me on this problem, it looks like kind of the path of least resistance to eliminate the z terms, okay? So let's go ahead and do that. I'm going to start by combining row 1 and row 2, just because it looks like it's easy. I can keep my numbers small. So I'm going to do 2 times row 2, which would be 4x plus 8y minus 2z equals 14. And then I'm going to add that to row 1, which is as is, just copying it. Okay, so let's add those together, and we'd end up with 9x plus 5y, 0 z's, which was the whole point, and then equals 17. Okay. So now I'm going to eliminate z terms again, and I have not involved row 3 yet, so I want to make sure that I do that, okay? So let's see, I'm going to multiply, how about if I multiply row 1 by -2? So, okay, so we'd have -10x plus 6y minus 4z equals -6, and then let's add it to row 3. Okay, and we've got -9x minus 5y plus 0z equals -3. Okay, now if you look at my new system of equations, so here's equation 1 and here's equation 2. Some folks can just eyeball it and tell that at this point I've got a no solution problem, but let's show what it looks like. At this point, if I just take equation 1 and add equation 2, so just add, these two equations together, I'd end up with 0x plus 0y, which is 0, and I'd end up with 17 plus -3, which is 14. So here's what math is telling us. Sure, you'll get all 3 planes to intersect in the same place as soon as 0 equals 14. Anyway, so this would be, it's this, again, just like with 2 dimensions, it's this universally false statement that is your trigger to realize that you were in kind of an impossible situation. There's these particular 3 planes just plain don't have any points in common. So your answer to this would just be, therefore, there is no solution. There we go. All right, my friends. Okay, let's move on to part C. And part C, I hope it makes sense. If you have 2, you can tell these are planes because they've got X, Y, and Z in them. And if you only have 2 of them, then, if you only have 2 planes, then really there's only 2 outcomes you could possibly have if you have 2 planes. The 2 planes could be parallel, in which case you would have no solution, or the 2 planes could intersect, in which case you would have a line in 3D space where the 2 planes have points in common. And so if you only have 2 planes, you're either going to have a no solution or an infinitely many solutions case, okay? And you can tell just by looking that these 2 planes are not parallel because not all the coefficients are the same. You've got 1 for the x's, those are the same, but you have +1 and -1 for the y's, and you have +1 and -8 for the z's. So that's a way to tell. You could just tell at a glance if they're parallel or not. So anyway, so this is going to be an example of an infinitely many solutions problem. And just want to scroll up and remind you of the directions here. It says, this is where this part applies, if there are infinitely many solutions, characterize the solutions in the form of an ordered, in this case, triple, in terms of 1 variable or a free variable. So we've done this in the past in 2 dimensions. Now you just get to do it in 3, okay? So go ahead and see how far you can get with part C, and then we'll talk about it in the next video.